Today we shall be talking about theory of relativity. At the end of these lectures, viewers will be able to explain relative motion, facts about relativity, Einstein's first and second postulate, relativity of time, time dilation, and solve problems on time dilation. Let's get started. But before I continue, I would like us to watch these videos. The first one is on relative motion. You can see a train moving at a high speed and two observers inside the train. To them, it appears as if the objects outside is on motion while they are stationary. That is to say that the laws of physics is the same everywhere. One of them now decides to drop and observe the train and sees the train to be on motion while he is stationary. Let's also watch the second video. This video is on time dilation. So assuming photon of light is allowed to oscillate in 1 second at a certain distance d, and of course you know that the speed of light is constant. Observe the oscillation is constant as well, equal distance and equal time. You now take the same oscillation of time to space. While inside the jet or the rocket, when you are in space, you discover that time slows down. So when an object tends to move with a speed close to that of the speed of light, it slows down time. You can see that the red line represents the time oscillation. So the more the object approaches the speed of light, the more the rocket approaches the speed of light, the slower the time oscillates. The more speed you apply towards the speed of light, the slower. Look at the red line. So this is what happens in space. So somebody who travels to space and returns after a certain time will tend to be younger than the person who was here on the earth if you are observing it from the surface of the earth. Okay, so that one is also a video on time dilation. Let's move to our class proper. Relative motion. If you look outside a moving vehicle, you will observe that every object lying stationary appears to be moving in the reverse direction. This explains the concept of relative motion, which is the first video. When we say an object has velocity or that object is moving on motion, or that object is on motion, then this velocity is with respect to what we mean by frame of reference, or you can as well call it the reference frame. In everyday life, the reference frame is the earth where we are into, or the ground. What we mean by the term reference frame is just about where you are observing an object from. Like, I am observing an object. I see it to be number 3, meaning that it's a number. And maybe my location is at the south. So I am looking at an object from the south. That object appears to be number 3. The observer who observes that object from the north or from the east or west will not see the same thing, but does not mean that what I am saying is wrong. Let's look at it from this perspective. I view the same object from the north. What the person at the north will see is a letter E. You view the same object from the east. What the person from the east will see is the letter W. I view the same object from the west. What the person at the west will see is letter M. So I started by saying that I was viewing it from the south. That is my frame of reference. The frame of reference. So what I saw was number 3. It's not different, but it's because of where I was looking at it from. That is what relative motion or relativity is all about. A person sitting in an airplane is at 0 velocity relative to the plane. You are inside the plane with a person. The person is sitting and not moving. You are also sitting and not moving. Both of you are sitting down. At that point, you see that you have no velocity. So you are at 0 velocity to the plane, or relative to the plane. But if you look at, or maybe you observe the plane from the ground, you will observe that the plane is moving at a certain velocity, and the people inside the plane moves at a certain velocity. That is the reference frame. Let's look at another example. Assuming you are traveling in a train, and the train is moving at the speed of 100 meters per second, then your speed, according to the other passenger sitting on that train, is 0, because according to him, you are not moving. So when you are observing another person inside the train, you are not moving, you don't have velocity. The person inside the train does not have velocity. You assume that your velocity and that of the person is 0, although the train is moving at a certain velocity, but it appears as if you are stationary. But if somebody standing outside the train observes you, according to him, you are moving at the speed of 100 meters per second, just as the train. Now, an observer sees the train moving. That observer is stationary and sees you to be moving at the speed of 100 meters per second. But when you are inside the train, it appears as if you don't have any velocity. But rather, if you look through the window, you see that those people outside, or those things, objects outside, will appear to be moving. Relative velocity. It depends on the frame of reference where you are observing an object from. It does not alter the laws of physics. The motion observed by the observer depends on the location where you are looking at it from, the frame of reference. The motion observed by the observer depends on the location, the frame of the observer. This type of motion is referred to as relative motion. What is this relative motion? Relative motion is simply the motion of a body A as observed by another body B, where B is the reference frame. I take it again. It is the motion of a body A as observed by another body B, where B is the reference frame. Where B is where you are watching it from. So the motion of a body, the first body in consideration, as observed by another body where you are standing, where B is the reference frame. Okay. The word relativity is coined from the word relate. Relativity is gotten from the word relate, which means in relation to, in proportion to something else, in relation to. Relativity tells us how things have importance in relation to another thing. So in relativity, you view importance of a particular thing, but you relate it to some other thing. That's just what relativity is all about. We are going to look at the first and second postulates of Einstein. The first one says that the laws of physics are the same in every initial frame of reference. The principles of relativity. The first postulate says that the laws of physics are the same in every initial frame of reference. The laws of physics are the same wherever you view it from. The law of physics holds. In anywhere you observe a particular law of physics, it holds. Like I started by we looking at relative motion. The people inside the vehicle appear to be stationary, while those outside are on motion. Now, somebody who is standing outside sees himself to be stationary, while the other one is on motion. We are also going to look at it from the perspective of the Faraday's law. But his postulate, the first one, says that the law of physics is the same in every initial frame of reference. Then the second one says that the speed of light in a vacuum is the same in all initial frame of reference and is independent of the motion of the source. I take it again. The speed of light in a vacuum is the same in all initial frame of reference, and it has nothing to do with the motion of the source. So if you see a moving bus and all of a sudden that bus ons the light of that bulb is independent of the motion of, the light of that bus is independent of the motion of that bus. Take for example, a bus is moving at a speed of 100 meters per second, and all of a sudden somebody stays on that bus and shoots a bullet. Then one could say that the speed of that bullet would be the speed of the bus plus the speed of the bullet. But that law does not hold in terms of electromagnetic wave or light. That you are in the bus that is moving at a speed of 100 meters and all of a sudden you on the light and it travels at the speed of light. You cannot say 100 meter speed of the bus plus the speed of light is equal to is wrong. That's what Einstein was trying to postulate here. He said that the speed of light in a vacuum is the same in all inertial frame. Whether you are inside the bus and you see the speed of light, it is the same. Whether you are an observer observing the bus and the light coming out from the bus, it still has the same velocity. I take it again. The speed of light in a vacuum is the same in all inertial frame of reference and is independent of the motion of the source. Let's proceed. In terms of the first postulate, let's look at Faraday's law. Looking at the picture here, let me use my marker. Observing this picture, at this point, you see that when this bar magnet is introduced into this coil, there would be a flow of electric current. Okay? There will be an indication that there is a flow of current here. If you decide to remove the bar magnet, current will still flow. That is the first frame of reference. Now, you now decide to allow the bar magnet to be constant and you move the coil. You move the coil to where the bar is. You still have the same amount of EMF flowing, the same amount of deflection. You now decide to remove the coil from where the bar was located. The same amount of current flows, the frame of reference. That was what Einstein was trying to say, that no matter where you are looking at it from, the law of physics holds. Are you following what I'm trying to say? Okay. Then the second postulate. I made mention about a moving vehicle, but in this case, this one is a moving rocket and is moving at the speed of 100 meters per second. And all of a sudden, it decides to project the missile here at 100 meters per second. What will happen is that the velocity of the missile would be, okay, this was 1000. Okay, so the velocity of the aeroplane here is 1000. And the velocity of the missile here is 1000 plus 1000. The total velocity would be 2000 meters per second. But this principle does not hold in terms of the speed of light. You cannot say the velocity of the rocket plus the speed of light. It does not hold. That's what the second postulate is all about. So Einstein's second postulate is that the speed of light in vacuum is the same in all inertial frame of reference. Whether you are observing the speed of light from the jet or you are outside and observing the jet moving, the speed of light is the same. It does not change, and it's independent of the motion of the source, and it has nothing to do with the motion of the source producing it, whether it is a jet or a rocket or a bus. Okay, let's continue. Relativity of time dilation. This was the second video we watched. Time dilation. Time dilation, in the theory of special relativity, is the slowing down of the clock as determined by an observer who is in relative motion with respect to that clock. You can remember the video. Time dilation in the theory of special relativity is the slowing down of the clock as determined by an observer who is in relative motion with respect to the clock. We can as well define it this way. It is the slowing down of time relative to an observer who is in motion to another observer. It is the slowing down of time relative to an observer who is in motion to another observer. You can as well define it this way. It is the difference in elapsed time as measured by two clocks due to relative velocities, gravity, and general relativity. It is the difference in elapsed time as measured by two clocks due to relative velocities, gravity, and general relativity. Time dilation occurs because it is relative to another observer. It depends on the reference frame. Are you following what I'm trying to say? So time dilation occurs because it is relative to another observer, and it depends on where you are looking at it from, the reference frame. It is the slowing down of clock which is experienced by an observer who is in motion with respect to that clock. The slowing down of clock which is observed by an observer who is in motion with respect to that clock. The twin paradox. In the twin paradox, it really illustrates facts about time dilation, that you have two twins. You have a pair of twins, and one of them is an astronaut, while the other works with NASA. And the one who is an astronaut decides to go on space travel. The astronaut decides to leave on a deep space trip, traveling at 95% the speed of light. Upon returning, the astronaut's clock has measured 10 years, so that the astronaut has aged 10 years. After he has gone and returned, his own clock shows him that he is just 10 years old. These are identical twins. One is working somewhere in NASA and the other one is an astronaut. And the one that is an astronaut has decided to go to space, and he has his own time. And he comes back. To him, he has spent 10 years. However, when the astronaut reunites with his earth-bound twin, the astronaut sees that the twin has aged 32 years. they have now decided to reunite. When they met, the one that returned is 10 years old, while the other one who was on Earth is 32 years. This explains, or this is explained due to the fact that the astronaut's twin is traveling at a relativistic speed, and therefore his clock is slowed down. I started by showing you a certain video. When you travel at a speed close to the speed of light, time slows down. Because the speed of light is constant, and the distance of oscillation of that time is constant, but the oscillation of that light, the time of the oscillation was slowed down. This was illustrated in that video you watched, the second video. So it tells us the facts about the twin paradox. So you see, these are identical twins. They shake hands. This one is about to travel. This one is about to travel. It's the A here. He leaves the brother on Earth. As Speedo left, he leaves his brother on Earth. Both twins are the same age. They have the same age. So one has decided to embark on this journey. When Speedo returns from his journey, Gaslow is much older than Speedo. So on arrival, the astronaut discovers that he is much younger than his brother. You can see this other one with a gray hair. According to the picture, if you can see from there clearly. He has a gray hair. Okay, let's continue. Look at this figure. Moving clock runs slower. To an outside observer, the crew of the spaceship traveling close to the speed of light will age less than the people on the Earth. So you see the clock here. This one is about, look at the figure, the brown space here, tells you of the extension of time. So here the time travels faster. This person who is in space, his own time is slower. So the more you travel at the speed of light, the more time slows down. The slowing down of time relative to the clock of the observer is referred to as time dilation. Clock runs slower in high gravity. The spaceship entering a high gravity field like that of the black hole will experience even less time. You see a spaceship. At this point, look at this ship here. While it was traveling and it entered a high gravity hole in this other figure here. observe the time here, it is even more slower than what it was previously, even when compared to the time of the observers from the Earth. Time dilation. Okay, still waiting to move to the next slide. Still loading. Still loading. Time dilation calculation. The mathematical expression for time dilation is represented in equation 1. So the change in t represents time observed in the other reference frame, which is the Earth, or you can call it observed time. So change in t is the observed time. T naught is the time in observer's own frame of reference. You can call it the rest time or the proper time. Here in the expression we are using u. Either you use u or you use v, still the same thing. Represents the speed of the moving object. C is the speed of light in a vacuum. Still waiting for the slide to load. Let's consider this example. The proper time interval between two events as measured is 2.20 times 10 to the power minus 6 seconds. Since the two events are at the same position relative to 1, estimate the observed time, assuming u squared over c squared is given by the value 0.9801. They both have no units because it is a ratio of two velocities, so that was why the unit was lifted. Look at the example. Read through the question. I have given you the mathematical expression, so it is left for you to observe what, or to note what they mean by proper time and observed time. If we are going back to the expression, you see the observed time, change in t, proper time, t naught. If you don't call it proper time, you call it the rest time. Okay, so we have come back to the equation. I want you to study it properly. U and C was not given separately. Maybe if it was given separately, we would also do the computation that way. But in this case, it is a whole value. The answer is below. I just wrote the answer in seconds. You can apply the mathematical expression and then you test your knowledge to see if you are correct. This is the method. Solution. Change in t, time observed in the other reference frame, which is the Earth, or the observed time. T naught is time in observer's own frame of reference, the rest time, or you call it the proper time. U and V, or U or V, the speed of the moving object. c, the speed of light in a vacuum. When you apply this expression, substitute the values according to this expression, this is what you will see. Now use your calculator and compute this. Check if it will give you the answer we have here. Okay. Assignment. 2 characters are concerned or involved here, Robert and James. Robert, who is standing on the ground, starts his stopwatch at the instant, and James flies past Robert in a spaceship at the speed of 0.600 c, which is the speed of light. At the same instant, James starts his stopwatch. A. As measured by Robert's frame of reference, what is the reading on James' stopwatch at the instant that Robert's stopwatch reads 10.0 seconds? Which one is the correct answer? I, 10 seconds. I, less than 10 seconds. I, greater than 10 seconds. The second question is, or the B side of it says, as measured by James' frame of reference, what is the reading on Robert's stopwatch at the instant that James' stopwatch reads 10.0 seconds? I, 10.0 seconds. I, less than 10.0 seconds. I, greater than 10.0 seconds. So you are going to use the writing material, copy out the assignment, think about it, and tick the correct option. This one says, the proper time interval between 2 events as measured is 2.20 times 10 to the power minus 3 seconds. Since the 2 events are at the same position relative to 1, estimate the observed time, assuming u square slash c square equals to 0.9801. Thank you for watching Supreme Online Lectures. Please, I would like you to subscribe to our channel. If you are yet to do that, like it and share. Have a wonderful day.